And let's start with the intro of our third place winner team.
Yeah, my name is Dmytro Poplavskiy. Should I present slides as well, or just intro at this stage?
We can do a quick intro around the
Okay.
yeah, thank you.
Yeah, so I really enjoy doing Kaggle competition, and thank you very much for hosting it. It was a great pleasure to participate, and really happy to know that it's actually used and useful. Oh, thank you. Competitions. So the approach is inspired by Dmytro. Its idea to use CNN and the transformer for object detection. So I try to do something similar. So the solution has video encoder, which is based on PSM or 2D plus 3D, or like anything suitable for video encoding and provide some kind of activation. And then to use the decoder based on transformer to combine video activation and tracking features from multiple players. And this is probably where my approach was a bit different from most of other solutions I have seen. So in most cases, the solution was based to do prediction based on pairs of players to tell, like, do we have contact between those two players or not? While in my case, I did solution for single player to predict for some period of time, usually like 1 or 2 seconds, for current player and all players around. It usually I use like 7 players.
Dmytro, are you sharing your slides? Are you changing slides? Because we still see the first one.
Yeah, I'm changing up. Sorry, I will.
Oh, got it. Yeah, perfect. Thank you.
Yeah, it's probably was background window. Yes, so this is what I have for the model. The model is based on combination of video encoder, like usually CNN based, but could also be transformer based. It's something which would work well for video action recognition kind of tasks. And on top of this, to use transformer decoder to use attention mechanism to query different parts of video or features from different players around the current one. And for yes, how I mentioned that my approach is a bit different because I used prediction for simple player and predicted for everything around current player. So here's an overview of the model. It looks much more cluttered than it actually is, but the first part is video encoder. When I supply number of video frames, usually every second or every third frame, for video encoder for both end zone and sideline videos. At the output, I have activations for every step. So it's downsample to step timestamps for every steps on both video frames centered around the current player. And for every activation, I also added position encoding and encoding for the frame number and some kind of markers to be able to separate, is it sideline or end zone video. So this is first input to the transform encoder. Another input is I selected some features for the current player for number of timestamps. And for every timestamps, I selected what's the nearest other players around and used similar kind of input features. And then I had a couple of iterations of transformer encoder. Like the first stage is to do query of transformer encoder over the video inputs, video activations from the same step. And the next step would be self-attention over all players or all timestamps. And this is repeated a couple of times. And after this, we can directly predict using activations, do we have ground contact for the current player, and combining features, activation of the current player with all the other players. We are predicting, do we have contact between those pairs of players? So actually for every contact, we would have it averaged for prediction for one player and for another player. And features-wise, it's essentially what I'm feeding to transformers as inputs for every player. So first one is position encodings for helmet position on the video frames, and it's a way for transformer to select which part of image to query. And this feature actually works. I accidentally used like removed it, and the performance of model dropped quite significantly. Also the same for encoding for the step number. So also a couple of features. Is a player in the same team as the main player we're querying? Is this the selected player with the distance, both like one hot encoding and position of this player, and a couple of frames, speed, acceleration, relative orientation of the current and selected players. So I tried to be a bit careful here. Like it's quite easy for transformer to overfit to those features. So I selected some small subset of feature which makes sense to me and which improves the score. Since it's end-to-end solution, the training is quite straightforward. It's a single stage, so it's simple, like low loss, and we don't really need anything more fancy. And ensembling is just averaging prediction from multiple models or from the same models, but prediction over overlapping slices in time. I used false cross-validation and split by game. I haven't shuffled the game, so I tried to sort games by name to see if I can pick up any problems with generalization maybe on some future games. And I have seen quite a bit of difference between faults. So on some faults, some model perform better, or some ideas, and on other faults, worse. And so this may indicate there are quite a bit of noise probably on leaderboard, and I expected a bit of shake-up. And it's also looks like increasing the data set, annotation data set, it should be possible to improve the performance of models, at least by looking how models are overfitting. Next, I will discuss some interesting findings during this competition. So this model, it was almost my first try, and it worked reasonably well. So how we try to improve it, I was hoping by fixing the baseline helmet to player assignments, I could improve the score. Because like the previous competition result was like very impressive, but it's still like I was hoping there are some games when there are obvious mistakes. So what I try to do, I try to fit perspective projection between helmets and tracking data, and in a way to for such projections to be continuous and smooth between frames. And if I see some players not fitting this projection, so predicted position on the screen quite far from the actual detect position, I remove this from assignments and try to reassign everything, like all unassigned players, to find a better fit. And it works for many games, but it still failed for many others, especially this approach, because it enforces consistency of transformation between players. It can get stuck in bad solution, and then the rest of the game would be quite bad. So I tried to use not only the tracking data and already supplied annotations for helmets. I tried to estimate the flow, essentially how camera moves. So I used already previous projections to predict the flow of the points on the field without players. And I trained a model to predict such flow. And then I could use this flow to enforce this continuity of transformation between frames. And visually it solved like almost all cases when model make mistakes. So, and usually it's like at the end of the game. So you see like a couple of examples when not like those assignments for my predictions, those players were like on completely different part of the games. And there was also some assignments of players not involved in the game. But after enforcing this reassignments and for transformation to follow the camera flow, you see in this case, all the players are found like exactly. And visually, like this approach solved most of issues, most of front assignments. And impact was smaller than expected. And potentially this one of the reasons, because we have two video frames from both sideline and end zone, and model would learn to check both of them. And still, like most of games were quite good. And so, yeah, I have seen on some falls up to 0.5%, which was quite significant. But on private tests, I have seen almost no impact. So, yes, I think it's very interesting finding, and it's a part I quite enjoy doing. This is more related probably to the previous year tasks than to this one. Okay, for the simple model, like ensemble is very trivial. It's averaging of a couple of similar models. So if I used only one model, it's comparison of the score. It's like probably difference is 0.4% between them, between same models, ensemble and single model. Okay, that's all for me. And if you have any questions, I would be very happy to answer.